Okay, we can go ahead and get started with problem 2.6 from Wald's General Relativity, where he wants us to, in part A, to verify that the dual vectors v mu star, as defined by equation 2.3.1, constitute a basis of v star. So the notation I'm going to use is like this. Lowercase v is a vector from the vector space v, and we're going to write them like this, a sum over a constant and basis vectors. And then we're going to say that u are vectors from v star, and we're going to write them like this. As some of the dual basis vectors, and then the idea is that v lower times v upper gives us this delta function between the two indices. And using this fact, we want to verify that these vectors are, or that these vectors do indeed constitute a basis. So let's go ahead and check that. So, okay, 6a. We need to show two things. In order to show that these vectors constitute a basis, we need to show linear independence, and we need to show that they span the space v star. So we'll start with linear independence. So in order to do this, let's consider a vector v from capital V, and a vector u from v star, written in terms of what we hope are the basis vectors. So we're going to take an inner product between u and v, and this is going to look like, let's see, aj, vj, ai, vi equals aj, ai, vj, vi, and this equals the a's times this delta function as we've defined it up here, so it's going to be delta of j and I now. And this is simply the sum over the i's like that. So if we are doing this for an arbitrary vector v, u dot v equals 0 only if u equals 0. And that's how we show linear independence, or I mean, we could also say only if the AIs equals 0. And then the next thing we need to show is that these vectors span v star. So let's do that next. Okay, so we're going to start by letting a vector from v star act on a vector from v, so we'll have u on v like this. And what we want to show, show that we can write u, acting on v as a sum of dual basis vectors acting on v. So this, in essence, will show that no matter what u is, we can represent it as these dual basis vectors, and therefore they span v star, because u can be any vector from v star. Okay, so let's start actually working this out. So this is going to look something like u of ai vi, or we could pull the ai out like this. But remember that ai is nothing other than something like this, because the v's will evaluate to a delta. So with this, u acting on v is And okay, with this we can get v back here. So we get vi times v u on vi. Now we're free to pull this v out. Acting on v. So now what we've essentially shown is that u acting on v is the same as this expression here at the bottom. Or in other words, we were able to write u as a sum of these, what we hoped were the dual basis vectors, times the linear functional evaluated on vi, acting on v. So essentially we've proven here, let's say, wrote linear, oh sorry, what am I writing? Oh my goodness. Wrote linear functional as a sum of the, quote, dual basis vectors times constants. Therefore, the v, or actually, yeah, the vi span v star. And that's it. That's all we have to show for part A here. Okay, now for part B of the same problem, Wald wants us to take these with the lower indices to be the basis for the vector space V, V's with the upper indices, I've been omitting the stars, to be the dual basis, letting W belong to V, omega belonging to V star, and showing that we can write omega and W as these two expressions here. So remember, W belongs to V, and omega belongs to V star. Okay, so let's start with W. W equals Wi Vi, where these V sub i's are the basis vectors, but we also know that Wi is simply Vi Wj Vj, because the V's will evaluate to a delta and bring this j to be an I. So therefore we get here Vi Wj Vj V sub I. And then we notice that what's in the brackets here is just W, so we get Vi W Vi, where there's an implicit sum over the i's. I'm using Einstein summation notation, so I'm not putting the sums there explicitly like Wald does. Now for omega, we can write this again as omega I times Vi. But we know that omega I is nothing other than omega j Vj times Vi. So therefore we can rewrite this expression as follows: omega j Vj times Vi Vi. Now the expression in the brackets out front here again is just omega, so we get omega times Vi Vi with an implicit sum over the i's, and we have shown what we were asked to show for this section. Okay, finally for problem 6c, Wald wants us to prove that the operation of contraction, which is equation 2.3.2, is independent of the choice of basis. So that equation looks something like this. He says that the contraction of a tensor T is just that tensor T with a slot replaced with the dual basis vector, and a slot replaced with a basis vector. Now trivially we can go in and multiply by 1, so we can go u delta here, and it changes nothing. And u delta up is an element of the new dual basis, or a new dual basis, and u delta down is an element of the new basis. And we're going to do the same thing here. We'll just use a different dummy index. We'll use gamma. Okay, now thanks to the linearity of the tensor map, we are able to pull vectors out of these slots here. So let's go ahead and take out v sigma both up and down to begin with. And then we'll pull out u lower delta and u upper gamma. And so doing this leaves u upper delta here, and u lower gamma here. Now, this is just going to be 1, and this is going to be a delta between delta and gamma. So we'll just apply that in rewriting t here. So t, we're going to apply it to the first t we see. So we'll let this become u gamma. And then we get u lower gamma here. And we'll notice that this is nothing other than ct that we started with. Therefore, contraction doesn't depend on choice of basis. And we're done the problem.